Alright, this is the last presentation on derivatives. We've seen the concepts, we know that the derivative is the slope of the tangent line, we know that derivatives can be used for optimization to figure out where the slope is zero, where the maxima and minima are. We've seen how to use different derivatives when we're graphing functions. All that conceptual stuff is there. The last thing that is missing is the last few differentiation rules that we need. So let's push that through. It's just rules. We know what else to do. Let's get it done. So, how do I find the derivative of something like the inverse cosine function? Well, if I just write down y equals arccosine of x, that gives me no idea how I could find the derivative. But if I solve for x, if I say cosine of y equals x, which is the same thing, that can be differentiated with implicit differentiation. So I take the derivative on both sides. I get negative sine of y times y prime is equal to 1 on the right side. And that means that y prime is negative 1 over sine of y. But if we start with a function of x, then the derivative should also be a function of x. And so y prime we know is negative 1 over sine y. Well, that's negative 1 over sine of arccosine x. So if I can replace the sine with a cosine, I would be in business. And of course the sine is replaced with a cosine by realizing that sine of anything is square root of 1 minus cosine squared of that anything. So here we get negative 1 over square root 1 minus cosine squared of arccosine of x. And that's negative 1 over square root 1 minus x squared. Okay, so we don't want to go through implicit differentiation all the time when we're taking derivatives of inverse functions. And in fact, ideally, we don't even want to use this theorem. But at least for the derivation of these derivatives, this theorem can be helpful. You take a differentiable invertible function, so a function that passes the horizontal line test and which has no corners and no jumps or anything like that. Then the derivative of the inverse function is given by f inverse prime of x being 1 over f prime of f inverse of x. And even though that formula looks kind of strange, it's quickly derived, which is what we're going to do first, and then we're also going to look at the geometry of the whole situation, which is actually quite beautiful. So we know that x is f of f inverse of x, because if you plug the inverse into the function, you just get back what you started with. So take the derivative on both sides, you get 1 is the derivative of x, is the derivative of f inverse of x, is equal to f prime of f inverse of x times f inverse prime of x, just by the chain rule. And then we solve for f inverse prime, and we get that that's 1 over f prime of f inverse of x, because all that happens is we have to divide by this term here. Sorry, the highlighting really doesn't work too well in these PDFs. So that's that ought to be the theorem here. And well, what's the geometric side of it? I mean, here's a formula, and we'll use that formula to our advantage. Geometrically, it's actually pretty cute, because what we start with would be the original function, which is differentiable and therefore has a tangent line, right? And when you go from the function to the inverse, what actually happens is that you're flipping the x and the y-axis, right? You're interchanging x and y. Now, if we're interchanging x and y, we get the graph flipped over, and the original tangent line that was rise over run becomes run over rise, so the slope is now really the reciprocal of the original slope, but the diagram is labeled all wrong. So let's take the labels out and put the labels in that we would have for the inverse function. So now the x-axis is a horizontal again. X is here, and this is f inverse of x. And this is the differentiation formula, because the slope of this tangent line is still the reciprocal of the slope of f at this point here, which is f inverse of x. Okay, so that's the formula symbolically as well as geometrically. Let's take a look at how this thing works in action. So the derivatives of the inverse trig functions, and that's certainly a set of derivatives that you ought to memorize. Well, the derivative of the arcsine is 1 over square root 1 minus x squared. The derivative of the arccosine is negative 1 over square root 1 minus x squared. And the derivative of the arctangent is 1 over 1 plus x squared. Now, the second one we've done at the beginning of this presentation. The third one we actually did at the end of the presentation on implicit derivatives. And so that means we can just concentrate on the sine function, and it's very similar to what we did with the arccosine function. So the derivative of the arcsine is 1 over the derivative of the sine of the arcsine. So now we're using the formula, right? So that's 1 over cosine of arcsine of x, and now we have to turn that into something that is a bit more readable. And well, that would be 1 over square root 1 minus sine squared of arcsine of x, and that's 1 over square root 1 minus x squared. Okay, well, those are the derivatives of the inverse trig functions. The derivative of the natural logarithm, which is the other really important inverse function that we know, well, that derivative is just 1 over x, so that's kind of nice because it sort of fills a hole in the power rule. We'll look at that more carefully when we're integrating, which is coming up pretty soon too. Okay, so, well, because there is an absolute value, we have to consider x greater than 0 and x smaller than 0 separately. For x greater than 0, the derivative of the ln x absolute value is just the derivative of ln x. That's 1 over e to the ln x, right? Because the inverse function is e to the x. The derivative of e to the x is e to the x, and then we just plug in the ln here. And that's just 1 over x. Great. For x smaller than 0, well, for x smaller than 0, we have that x absolute value is negative x. So that means the derivative of ln x absolute value is the derivative of ln of negative x. And that would be, well, negative x is positive, and at positive x's we know that the derivative of the ln is 1 over whatever is inside, so it's 1 over negative x times negative 1 from the chain rule, and that's 1 over x2. Okay, so those are these new differentiation formulas. There's another theorem. Oh yeah, sure. Now that we have them, this is borderline theorem or example. Remember that we talked about the power rule, and technically we only had the power rule for rational exponents. Well, now we can work out the power rule for all real numbers except r equals 0. Well, actually r equals 0 fits the pattern too. It's just typically not thrown in there. Is that the derivative of x to the r is r times x to the r minus 1. So how do we prove that? Well, the derivative of x to the r is the derivative of e to the r times ln x. Sure. But that by chain rule is the derivative of the exponential just comes back, right? The derivative of e to whatever is e to whatever, times the derivative of the inside, which is r, times the derivative of the log, which is 1 over x. And, well, that is, well, e to the r times ln x is x to the r times 1 over x stays. And, well, x to the r divided by x is x to the r minus 1, so we get r times x to the r minus 1, just as the power rule should provide. So now we've got a power rule for all real exponents. Well, big deal, it still works the same way. If we wanted to find the derivative of an arbitrary log, or just say the logarithm to base 2 here, well, what we need to remember is that by the change of base formula, the logarithm to base 2 is the logarithm of x divided by the logarithm of 2. And so that means that the derivative of that would be 1 over ln 2 times 1 over x. And that is another reason why in the theory we prefer to work with the natural logarithm, because when we differentiate that thing, we don't have these constants to worry about. We just get 1 over x. Okay, what else do we have? Now the derivatives are going to get more and more complicated here towards the end, because I want us at least once to go through how bad derivatives can get and how much they can pile up on each other. Now, certainly, when things get too bad, you're going to use a computer algebra system. Let's not play pretend here. But we should be able to handle symbols at a pretty large and pretty complicated level, because that way anything that we may see in an advanced text isn't going to look so bad anymore. So if we were to find the derivative of ln of x squared minus 1 divided by 3x squared plus 2, well, here's the function. What would we do? We would take the derivative of the logarithm, and the derivative of the logarithm by chain rule is 1 over whatever is inside, and I'll just copy the inside of the logarithm into the denominator. And then we still have to take the derivative of the inside, and that's the quotient rule, right? Derivative of the numerator, 2x, times denominator, 3x to the 4th plus 2, minus derivative of the denominator. That should be more than that. Hang on. And we're back. Of course, 3 times 4 is 12 and not 4, so let's move on with that. So derivative of the denominator, 12x cubed. Yes. Oh, I was just thinking 12x squared. No, that's 4 minus 1 is 3. Come on, Doc, you can do this. Okay, so derivative of the denominator times the numerator divided by the denominator squared. And, well, now we keep simplifying. 1 over a fraction is, of course, nothing but multiplying with the reciprocal of the fraction. And if we multiply out the numerator here, we get 6x to the 5th plus 4x minus 12x to the 5th plus 12x cubed because of the double negative sign. Everything else stays the same. Don't try to multiply out the denominator. Anything that's factored has a chance to cancel, and we can see here this one will cancel against this 2, of course. Alright, so that gives us a denominator of x squared minus 1, 3x to the 4th plus 2 after the cancellation. And the numerator is just a negative 6x to the 5th, combining these two terms, plus 12x cubed plus 4x. And, well, that's it. It's not that hard if you do it right. This example looks, well, rather pitiful compared to the other one, but it's piling up on us in a different way, because here we have a product rule inside a chain rule, right? If we take the derivative of arc cosine x e to the x, we will need the derivative of the arc cosine, which is negative 1 over square root 1 minus whatever is inside squared, and whatever is inside is the x e to the x, which we plug in. And then what can sometimes happen is that people get so relieved about that that they forget that you have to use the product rule here. So of course this is first times derivative of the second, x e to the x, plus e to the x. There, see? E to the x. Okay, and well, that's already it. There isn't much else you can do with that one in terms of simplification. Yeah, you can factor out an e to the x maybe, but that's it. Okay, well, it seems my mistakes always come in twos, so let's hope that that's it in terms of mistakes. Let's take a look at one last example, and that's about as ugly a derivative as you can take reasonably by hand. But on the positive side, if you can handle something like that, you can handle just about anything. So let's take a look at the derivative of e to the x minus 5x cubed quantity squared ln of 4x squared plus 12. Well, I would want to be really careful here. That's the product, so we use the product rule. So it's derivative of the first times the second plus derivative of the second times the first. Now I take the derivative of the first, which by chain rule is 2 times whatever is inside, e to the x minus 5x cubed, times the derivative of the inside, and I'll just keep that, times ln 4x squared plus 12, plus, and now we still have the other one, which is 1 over whatever is inside the log, 4x squared plus 12, times the derivative of the inside of the log, 4x squared plus 12 prime, times, well, whatever was behind that, e to the x minus 5x cubed squared. Okay, and we can work that out too, because now we just take those derivatives. We get 2e to the x minus 5x cubed here, e to the x plus minus 5x cubed prime, that would be e to the x minus 15x squared. The ln 4x squared plus 12 is copied, and we have 1 over 4x squared plus 12 copied. Derivative of 4x squared plus 12 is 8x, and e to the x minus 5x cubed squared, that is just copied again. And then, well, if we want to, we can take out a common term, and that common term would be 1 of the e to the x minus 5x cubed, which leaves us with 2 e to the x minus 15x squared ln 4x squared plus 12 from the first term, and the second term keeps the denominator 4x squared plus 12 and 8x e to the x minus 40x to the 4th, because once the square is gone here, and there is a square here, it's just hard to see, then 8x times negative 5x cubed gives us a negative 40x to the 4th. Now that's really complicated, but you can see if you just doggedly keep track of what derivatives you still have to take, you can work something like that out. And for this one, I actually thought about it a little bit, and well, if you do this mentally, and if you want to figure out which rule to use, it's always good to pretend you're trying to evaluate this function with a scientific calculator. And so when you do that, you do all sorts of computations, but the last computation you do is that you multiply this term with that term. If you work this out with a, not with a graphing calculator, with a scientific calculator where you have to do all the operations one by one, then the last operation performed is that you multiply these terms. And that tells you that you first have to use the product rule. Okay, so you need the derivative of the first, and you need the derivative of the second. Okay, so now you have to figure that out. Well, the last operation you perform if you evaluate this is that you square everything, which means that you need the chain rule. And so that means inside that chain rule you've got an outer function, which is the square function. You've got the function that's plugged in, which is e to the x minus 5x cubed. So the derivative of the outer function is 2 times whatever is inside. The derivative of the inner function is e to the x minus 15x squared. And, well, now you put that stuff back together, right? You reassemble. The derivative of this function up here is 2 times whatever is inside times the derivative of the inside. And now you have to do the same thing on the other side. The last operation that you perform here, if you evaluate this with a calculator or mentally, is the logarithm. So you need to use the chain rule. Your outer function is the logarithm. Your inner function is the 4x squared plus 12. The derivative of the outer function is 1 over whatever is inside. The derivative of the inner function is 8x. You reassemble that, and, well, what do we get? We get 1 over whatever is inside, 1 over 4x squared plus 12, times 8x, and I already took the liberty of putting the 8x onto the numerator here. All right, now you reassemble that according to the product rule, and you get that the derivative is derivative of the first, all this stuff, times the second, coming from here, plus derivative of the second, times all the stuff from the first. And then you can simplify that, and you, of course, end up with exactly the same result as before. And that's it for differentiation rules. Sorry the last 2 presentations were a little rushed. I have to get these ready for a class, and even though I would have time to record those after I go to Germany, which will be the day after tomorrow, I'm not sure how awake I would be when I come back, so I thought I'd record those right now. So, you've got homework to do, but we are at the end of derivatives. Basically, there should not be any derivatives that causes you problems, except that it could become as complicated as, well, what we've seen here, and every so often there could be computational errors. I will make sure I'll read my next few slides more carefully so that that doesn't happen, but remember, the important thing is not to try to be perfect, because that's just not going to happen. The question is not if you or I are going to make a mistake. The question is when. The important thing is when it happens, we got to catch it. And I think we did that, and you're also pretty good at doing that for me when I'm teaching face-to-face. Let's keep it that way, and let's hope that whatever mistakes you make, you catch in time too. All right, Merry Christmas, because right now it actually is Christmas for me. It's the 22nd of December.